Hi everyone, welcome to the lesson on optimization. This is Professor Rosenthal, and today we'll explore how to determine maximums or minimums of a given problem situation. And that's what optimization is all about. Depending on the problem, sometimes you'll be finding maximums, sometimes you'll be finding minimums. And in all of those cases, you'll be provided with some constraints. So these maximums and minimums to optimize a given situation will be found subject to the given constraints. So let me give you an example about what I mean by that. So for example, they could tell you certain restrictions about the dimensions of the box. Maybe there's something where like the length has to be twice the width, or there could be certain kinds of restrictions. And within those restrictions, they could ask you to design a box that will contain the most amount of material. So maximize the volume, that is. Or they could give you a situation where they say, okay, we want to be able to put a fixed amount of volume, a fixed amount of, let's say, liquid in a cylindrical container. And then they'll ask you, okay, how would you design it so that you would end up using the least amount of materials? So in that case, you would be minimizing the cost of creating the container. In other words, you would be minimizing the surface area. So given the constraint, here they're giving you the volume, here they're giving you some relationship between the dimensions. They're asking you to either maximize or minimize a certain quantity. So that process is known as optimization. And this is a fantastic section, I think, because, with just a little bit knowledge of calculus, just basically knowing that when you set the first derivative of a function equal to 0, you're going to basically find candidates to be maximums and minimums. That's all you need to know to solve a wide variety of problems. So just let's say you're trying to maximize the volume function. So by just setting the volume function equal to 0, the derivative of that, basically you are able to locate the maximums and minimums. And from there, depending on the situation, you'll make sure that if you're looking for a maximum, that you did indeed find a maximum or vice versa. So that is the process, and let's take a look at step by step. How are we going to get there? So to find maximums and minimums, first step will be determine a function that is to be maximized or minimized. So it could be volume function you're maximizing or the cost function you're minimizing. Typically, we'll use the constraints to write this function in one variable only. So if it's a cost in terms of x and y, our goal is to get cost in terms of x only. And in this situation, you would be using substitution. If you know y in terms of x, if there are several variables, you will get rid of them and try to write the function to be maximized or minimized with a single variable such as x. Then we set the derivative of that function equal to 0 and solve for x. Of course, this gives us the critical points, right, as we learned in the graphing section. And these are your candidates to be maximums and minimums. So once you do that, because sometimes you'll be looking for a maximum, sometimes for a minimum. So how do you know which one is which? Well, you could create a sign chart for f prime like we did in the last section, or there's another approach we're going to use here, and that is you would take the second derivative. If the second derivative is positive, what that means is you have a concave up situation. So slope is 0 and concave up. That would mean that you have found a minimum of the function. On the other hand, if the second derivative is negative, that would mean you have a concave down situation, and the point that you found there with the slope equals 0 would represent a maximum. And typically, this step serves mainly as a check-in step. And one last thing, sometimes the maximum or minimum can occur at the end point of the domain. So if you have clear endpoints of the domain, check the function at those values as well. Since we learned in the examples of finding absolute maximum and minimum, that the absolute maximum and minimums can also occur at the endpoint. So whenever possible, we will also check those endpoints to see if one of them appear to be an absolute max or min for the function. And before we dive into our first example, again, I want to give you a little bit more intuitive explanation about optimization. So here we have, for example, the situation, a fencing problem. Okay, so you have a limited amount of fencing and you need to create 3 adjacent rectangular regions that will create one big rectangular region. And the question is, how would you create, what dimensions would you use for the length and the width of the outer dimension so that you end up enclosing the largest possible area within those 3 rectangular regions? And I'd like to show you, there's a nice little applet here. Let's see, optimization. Okay, here it is. So this is the limiting amount of fencing we have. In this situation, 1,200 feet of fencing. So this is an applet, meaning if you drag the corners a little bit, it's still using the same amount of fencing, but you see that the area enclosed has changed a little bit, right? So for example, if I go to the extreme case, I'm still using 1,200 feet of fencing. This is our constraint. But if you're trying to maximize the area enclosed within the 3 rectangular regions, you see this is not going to be your optimal solution, right? And if you go to the other extreme, this one doesn't seem like it's going to be the optimal solution either. The optimal solution in this case will lie somewhere in the middle, perhaps, so where you can enclose as much land as possible within the 3 rectangular regions. And I'd like to show you one more example of optimization. So in this situation, you are laying pipe, some under the water, some along the road, and laying pipe under the ground or under the water is more expensive. So the question is, if you're going to go from the island to the power station, you could try to do it all in one shot, all under the water, but notice the total cost like 21,000 plus. Or you could go directly down the water and then the rest of the way on land. That's $18,000. That's a little bit better. Or you could just try to connect somewhere in the middle. Notice the numbers here, they're getting smaller up to a point, right? Like roughly 17,000, and then they're getting higher again. So perhaps somewhere in here is your optimal solution. If you could go this amount under the water and this amount over the land, and perhaps that will give you the minimum cost for the situation. So our job will be to find a coordinate right there that will make the total cost of the job as cheap as possible, as low cost as possible. Okay, so we're going to begin with very simple examples, and then slowly work our way towards more complicated ones. And the simplest example I could think of was this one. Okay, so find 2 numbers whose sum is 20 and whose product is as large as possible. So you could, do this one just by trial and error, right? So you could say, okay, they have to sum to 20, so I could try 1 and 19, but the product is 19. Or I could try 2 and 18, they sum to 20, the product is 36. And through trial and error, and it doesn't take folks long. This could even be your first guess. You could say 10 and 10, and that's going to be 100, right? And it looks like at the moment, at least, it's going to be the largest possible product. So you have optimized the situation, the 2 numbers with the given constraint that the sum of the 2 numbers be 20, if you let the numbers be x and y. And you want to maximize the product, which is x times y. Okay, so this is your constraint equation on the top. This is the one you're trying to maximize or minimize. And I would highly encourage you for every problem. There's typically going to be 2 equations. One is a constraint, one is something you're maximizing or minimizing. Write that next to the one that you are trying to maximize. Like in this case, I said maximize the product. This one is your objective function. This is the one you want to end up in one variable only, and you're going to differentiate and set equal to 0. But first, use the constraint equation to solve for one of the unknowns. So y equals 20 minus x. And then we're going to substitute for y. So product equals x times 20 minus x. So basically now I'm using calculus to show you that indeed 10 and 10 is the best you can do, and that truly is the absolute best you can do in terms of finding the largest possible product. And yes, for this example, we did not really need calculus, but it's showing you the idea behind the optimization process, and you will use the same steps even when you're doing a very complicated example. So step number 1 really is finding a function you're maximizing or minimizing and getting that in one variable only. And it doesn't hurt to simplify that also. So 20x minus x squared is our product function. And step number 2 is take the derivative of that. Basically, we're looking for critical points. Take the derivative 20 minus 2x and set that equal to 0. If you solve this for x, you're going to get x is equal to 10. And once you get x is 10, go back to one of the simpler equations and solve for y as well. Y is 20 minus x, so y will be 10. And how can we determine or verify or check that this is indeed a maximum and not a minimum? Because anytime you set derivative equal to 0, potentially you could be finding maximums or minimums, right? So to double check on that, you would take the second derivative of the product function. So take it from here and differentiate. You get -2. So clearly that's a number less than 0. So if the second derivative is negative, that means it's concave down. And if it's concave down, that means the point that we found at x equals to 10 represents indeed a maximum for our product function. And sometimes when you find your second derivative for another problem, you may find something, let's say, such as negative 2x. Okay, so if this is for a different question. If you get something that has an x in it, in that situation, you would plug your x value into the second derivative and see if that value actually makes the entire thing positive or negative. In this case, p double prime was a constant, so it's negative everywhere, it's concave down everywhere. Therefore, it's guaranteed that the point we found actually represents a maximum for the product function. So just like we expected, 10 and 10 are the two numbers that will give the maximum product. And sometimes they'll say, what is the maximum value? So you would just multiply them in this case, or plug into your p product function and get the answer is 100. So pay attention to what you're asking. Are they asking for like the dimensions of a box, let's say, or are they asking for the maximum volume you can create with the given constraint? And you insert accordingly, whether it's the function value at the given xy, or maybe it's the x and y values that they're asking for. Okay, let's take a look at another example. This one will be our example about a fencing problem, a very typical question in this chapter. Okay, so I'll give you a moment to read the question and I will come back and discuss. So this was the original question that we saw in the introduction. So given the fencing that's going to go all around these three rectangular adjacent fields is 1,200 feet, what are the dimensions, the outer dimensions of this rectangular field that will guarantee us that we have the maximum area enclosed? For problems like this, it always helps to first label your sides, and there's so many different ways to do it. Like you could label this little bit of rectangle and this smaller rectangle's width as y. In this case, I labeled the entire thing y. As long as you're consistent and at the end you interpret your answer accordingly, you're going to be fine. Okay, so if we let the outer dimensions to be x by y, and notice if that side is x and this is x, this is x, and this is x. So they give us the perimeter. The total amount of fencing is the perimeter of this entire region, right? So that should be, so that side is y, this side is y. So we have 2y plus 4x is given. That's 200. So that's given 2y plus 4x. The sum of all the sides of the rectangular areas. And we're supposed to maximize the area enclosed. So that's length times width of the outer dimensions. So that's y times x. That's what we're trying to maximize. And remember, this is our objective function. This is our constraint. We are trying to get the objective function in one variable only. And then we can set the derivative equal to 0. So to do that, you could divide both sides of this constraint equation by 2. And solve for y. So first, in this example, I'm first subtracting 4x, and then I'm going to divide both sides by 2. So y equals 600 minus 2x. So y equals 600 minus 2x. And let's substitute that back into the area function. So area is x times y, where y equals 600 minus 2x. So our area function becomes x times 600 minus 2x. So instead of y, we have used 600 minus 2x. And before we differentiate, let's go ahead and simplify, because otherwise you're going to have to use the product rule, and there is no need for that if you simplify it first. So x times 600 is 600x. And then x times minus 2x is minus 2x squared. And at this point, we're ready to take the derivative. The derivative of this will be 600 minus 4x, and set that equal to 0. So I'm going to add 4x to both sides and divide by 4 to solve for x. So 600 equals 4x, x equals 600 over 4, or 150. And units were in feet, so this will be x equals 150 feet. And once you find that, to get y, it's easy. Just go back to this definition of y, which is 600 minus 2 times 150. So 2 times 150 is 300, minus, subtract from 600, you get 300. So here we have 300 feet for y and 150 feet for x. Those are the outer dimensions. And if they ask you, what is the maximum area you could possibly enclose? So those are the dimensions. And the maximum area is x times y in this case of the outer dimension. So you multiply 150 times 300, or 45,000 square feet. And how do we check our answer? take it from here, take the second derivative of the area function. So just to differentiate a prime once again, so that's going to be -4. Once again, it's negative, so it indicates concave down. Therefore, with the point that we found, indeed is a maximum. And again, be careful whether they ask you for the dimensions or whether they ask you for the maximum area you can enclose. Accordingly, you will enter the answer in Edfinity or any homework system that you might be using for the current semester. Okay, I'd like to give you one more fencing problem to practice what you learn here. And then once you feel strongly about that, we'll move on to another type of problem. And my recommendation always is in this section, whatever type of problem you learn, try to do another one of just the same kind right away. And that way you're going to, feel a lot stronger, I think. And then you're going to build your knowledge on a strong foundation. All right, so this is the problem. I'll leave it on the screen for a moment, but we'll take a look at the solution to this problem in the next segment.